Section 3.2, polynomial functions. I would take a minute and pause this and go ahead and write down all these definitions and then play it and we'll discuss them. Let me first give you an example of a polynomial function. A polynomial function could look like this. F of x is equal to 3x to the fourth plus 2x cubed minus x plus 17. Okay, just an example of a polynomial function. Now, let's talk about these three definitions. The first is the leading term. The leading term is the entire term that has the highest exponent. So in this example of a polynomial function, my leading term is 3x to the fourth. All right. The leading coefficient is the coefficient or the numerical value of the leading term. Well, I just noticed that my leading term is 3x to the fourth. That coefficient that is in front of that term is a 3. So my leading coefficient is a 3. Degree of a polynomial in this form that I have up here, which is called standard form, okay, that's when everything's multiplied out and you write it from highest to lowest powers. The highest exponent is the degree. So in this example, the degree of this polynomial is 4. Now, there are cases where sometimes you're going to get the polynomial in factored form. Okay, when it's in factored form, you have to add up the multiplicities to find the degree of the entire polynomial function. And degree is also important because it tells us the maximum number of zeros and x-intercepts for that particular function. Now let's discuss some properties of polynomial functions. The first property is that the domain is all real numbers, okay? Negative infinity to infinity. Polynomial functions are also continuous, smooth curves. So let me just show you some examples. A parabola, a basic parabola, that is a polynomial function. Your basic x cubed is a polynomial function. So notice they're continuous, they're smooth, and their domain is negative infinity to infinity. Okay? They can also look crazy like this. All right? Again, those are some examples of what polynomial functions may look like. Another key factor or key point is that maximum number of turning points is the degree. Okay, remember the degree is the highest power minus 1. And when we're talking about turning points, we're talking about right here, if you look at this graph, all of these turns where it's getting increasing and then decreasing, or decreasing and then increasing. Okay, so we can figure out how many turns it could have by taking the degree minus 1. Again, that gives you the maximum number of possible turning points. Now we're going to discuss what's known as the leading term test. The leading term test is going to tell us about the end behavior of polynomials. So what's happening on the far left-hand side, okay, towards the x values of negative infinity, and what's happening on the right side, so when x values are close to infinity. Okay? In order to determine what's happening on the end of these functions, we only need to look at the degree and the leading coefficient. So we only really need to figure out what the leading term is. Now, we have 4 cases. The first case is if there is an even degree with a positive leading coefficient. An even degree with a positive leading coefficient. So here's a basic example. Your function could be f of x equals 1x squared. So notice this leading coefficient is positive and the degree is even. Okay? Well, let's think about what 1x squared looks like. I know that x squared is a parabola. Okay? So if I know that this is the most basic example of a function with an even degree and a positive leading coefficient, and I know that that is a basic parabola, then every polynomial function that has an even degree and a positive leading coefficient is going to have end behavior that is the same So it's going to go up and up on the left-hand side, up on the right-hand side. So again, that is the case for every polynomial that has even degree and positive leading coefficient. So let me just give you another example. Your polynomial could be something like f of x equals 3x to the 8th plus 2x cubed minus 3x plus 1. Again, we're only concerned with this leading term. It has a positive leading coefficient and an even degree. So this polynomial would also go up and up on the ends of the function. The next scenario I'm going to talk about is when you have an even degree and a negative leading coefficient. So your most basic function that has even degree and a negative leading coefficient would be f of x equals negative 1 x squared. So the only difference between the last one and this one is we have now a negative leading coefficient and an even degree. Okay, so even degree and negative leading coefficient. Well, we know that when we have a negative out in front of that function, it's going to flip it. Okay, it's going to reflect it across the x-axis. So that function is a parabola flipped upside down. So every polynomial function with even degree and a negative leading coefficient is going to go down and down. Down on the left, down on the right. Continuing on, let's go ahead and look at polynomials that have an odd degree. So these are my last two cases. If you have an odd degree with a positive leading coefficient, an example would be f of x equals 1x to the first. Okay? Again, we have a positive leading coefficient and we have an odd degree. All right, I know that this f of x equals 1x to the first, I know it looks a little funky, is simply the line y equals x. Okay, the line y equals x. I know that y equals x looks like that. Okay, so just from knowing what y equals x looks like, I know that every polynomial function with an odd degree and a positive leading coefficient is going to be going down on the left and up on the right. Now you can probably guess what's going to happen when we have an odd degree and a negative leading coefficient. So our last scenario. So that was scenario 3, this one's scenario 4. Now, our basic example would be f of x equals negative 1x to the first, which I know is the same as y equals negative x. So this is a negative slope. Okay? So the graph of that would be a line with a negative slope going through the origin. So every polynomial function with odd degree and a negative leading coefficient is going to go up on the left and down on the right. So notice that they are opposites. Okay? Notice they are opposites. Odd degree polynomials, the end behaviors are going to go in opposite directions. Okay, and then you need to know the difference between if the leading coefficient is positive versus negative. Okay, so recap, we have 4 scenarios. We have it going up and up, down and down, down and then up, or up and then down. The next key part of polynomial functions that we want to examine are the roots, or the zeros, or the x-intercepts. And when you hear roots, zeros, and x-intercepts, I'm essentially talking about the same thing. I'm talking about where it's crossing the x-axis. Okay? Now, once I've decided where this polynomial function is crossing the x-axis, I have to look at what's called the multiplicity, okay, or the power of that root. All right, let me give you an example. Let's say you have f of x equals x minus 2 to the third times x plus 1 squared. All right, this can be multiplied out. Okay, I can distribute and FOIL this out, and I would get the function in standard form. This is what is called factored form, okay, that I was talking about earlier, factored form. When it's in this form, what I can do is I can see what the roots are. Well, x minus 2, what is going to make that equal to 0? Well, the root would be 2. 2 minus 2 is going to give me 0. The other root, we have x plus 1 squared. What would make this 0? Well, negative 1. So those are my roots. Now, the multiplicity is the power that's associated with that root. So let's look at the multiplicity for a minute. The multiplicity for the root of 2 is 3. And the multiplicity for negative 1 is 2. Now, by definition up here, it says if the multiplicity is odd, then it's going to cross the x-axis at that 0. If the multiplicity is even, it's going to touch the x-axis. And we're going to see that as we graph these and as we go through some more examples. Defined all of the important terms for polynomial functions, let's dive into some examples. Example 1, find the degree, the leading term, and the leading coefficient of the function below. So my function is f of x equals negative 7x plus 11 plus the square root of 2x cubed. So we need to find the degree, we need to find the leading term, and we need to find the leading coefficient. Now remember, the degree, this here is in standard form. Nothing's factored, so it's in standard form. The degree in standard form would be the highest power. In this example, the highest power is cubed. So the degree of this polynomial is 3. The leading term is the term that has that highest power. So the leading term in this example is the square root of 2x cubed. And the leading coefficient is the coefficient of that leading term. So the leading coefficient is simply the square root of 2, the numerical value that leads that highest powered term. For example 2, we're going to describe the end behavior and the maximum number of turning points of the polynomial function f of x equals negative x squared plus 4x plus 12. Okay? So first thing we need to do, if we're talking about end behavior, we are doing what's called the leading term test. All right, so that refers back to our 4 scenarios. So we need to look at just this leading term, okay? My leading term is negative x squared. Now, I need to look at the leading coefficient, which in this case is a negative 1, and I see that that is negative. So I have to determine if that's negative or positive, and in fact it's negative. And I also have to look at the power. Okay, the power in this case is even. So if I have an even degree, so I'm going to write that out for you, even degree, and a negative leading coefficient, remember that that's telling me, if you look back at your notes, that this function, this polynomial, is going to be going down and down on the ends. Okay, so this is the end behavior. Down and down. Down on the left, down on the right. Okay, so that's part of your answer. And then it also asks for the max number of turning points. What is the maximum number of turning points that it can have? Well, remember, you take the degree and subtract 1. So the degree of this polynomial is 2. So 2 minus 1 is 1. So the max number of turns for this polynomial is 1. And we know that this function right here is going to be a parabola, okay? It's an x squared function. So we know that it's going to be going down and down, and it can only have 1 turn. Example 3. Use the function f of x equals 2x to the 4th minus 8x squared. List each real zero and its multiplicity. Then determine whether it crosses or touches the x-axis at each 0. So we're dealing with this function, f of x is equal to 2x to the 4th minus 8x squared. In order to determine the zeros, we have to get this in factored form. Right now we're in standard form. So we have to factor this. Now, the first thing you always want to try to do is, when you're factoring, is pull out a greatest common factor. In this case, my greatest common factor is 2x squared. So I'm going to go ahead and factor a 2x squared, and that leaves me with x squared minus 4. Now I look at this and see if I can factor a little bit further, and I can. So I can. So that leaves me with 2x squared. Now this x squared minus 4 is a difference of squares. So it factors to x plus 2 and x minus 2. Please refresh on factoring a difference of squares if you don't remember that. Now that we have our function in factored form, I can figure out my zeros. Okay? So we have to list our zeros. And then I'm going to list the multiplicities that correspond. And then if it crosses or touches. So we're going to make a little chart. Now, each term that has an x in this factored form, we have to set it equal to 0 to find the zeros. So my first term is 2x squared. When I set that equal to 0, I'm going to go ahead and divide both sides by 2. So x squared is equal to 0. Square root both sides, and that's going to give me x equals 0. So 0, plugging 0 into here is going to make this term 0. So that's my first 0, or my first root. I'm going to take my next factor, which is x plus 2, set that equal to 0 and solve. That's going to give me x equals negative 2. So that's my next 0. And then my last one, x minus 2, set that equal to 0. That's going to give me x equals positive 2. So I have 3 zeros, or 3 roots in this problem. Now, the multiplicities are the powers associated with it. So this first one, this first 0, so I'm looking at this 2x squared term. The multiplicity is a 2. X plus 2 is raised to the first power. I know we don't normally write that 1 there, but there is a 1, so the multiplicity is a 1. And same thing for this x minus 2. It's x minus 2. Really, there's a first power there, so its multiplicity is also 1. Remember, if the multiplicity is even, so I'm going to write that here, if it's even, it's going to just touch the x-axis and turn around. If the multiplicity is odd, it's going to cross, and this one is also odd, so it's going to cross. So it's going to touch at 0, it's going to cross the x-axis at negative 2, and cross the x-axis again at positive 2. Example 4, sketch the polynomial function using the leading term test and the y-intercept. So we have to use the leading term test to find the end behavior of this function. And then we're going to find the y-intercept, and we're going to give a sketch of what this graph of this polynomial could look like. It's not going to be definite, but it could look like this. So, first thing we need to do is we need to do the leading term test to find the end behavior. All right, so the end behavior, remember, we have to look at just the highest powered term, okay? So in this case, it's x to the 6th. The leading coefficient is a 1. So the leading coefficient we see is positive. The degree is even. When we have a positive leading coefficient and an even degree, I know that the graph is going to go up and up on the ends. Okay, it's going to go up and up. Now, the next thing we need to do is find the y-intercept. Remember, to find the y-intercept, that means you're going to plug 0 in for x. So that's going to give me f of x is equal to 0 to the 6th minus 7 times 0 to the 4th plus 7 times 0 squared plus 15. When I work that out, that gives me f of x is equal to 15. So my y-intercept is now 0, 15. Okay, so it says to use this y-intercept and what you know about the end behavior to go ahead and do a sketch of this polynomial function. So I only know really 3 pieces. So let's piece them together. I know the graph is going to cross the x-axis, the y-axis at 15. I also know the graph is going to end going up on the left-hand side and the right-hand side. Now, I don't know exactly what this looks like, and in fact, I don't know what any of the x-intercepts are, okay? So I only know where it's crossing the y-axis and what it's doing on the ends. But what I'm going to do is I'm going to show you guys really what it would look like, okay? And again, this is just a sketch of what you think it could look like. It might not be perfect. And this is really what the graph looks like, okay? The key is it has to cross the y-axis at 15, and it has to go up on the left-hand side and up on the right-hand side, okay? Again, that's an idea of what the graph of the equation f of x equals x to the 6th minus 7x to the 4th plus 7x squared plus 15 could look like. For example 5, we're going to use the function f of x is equal to 5 times the quantity x plus 2 squared times the quantity x minus 3. So notice that this function is in factored form. Okay, so I'm just going to write that over here to refresh your memory. This is factored form. If it was multiplied out and distributed, it would be standard form. So part A wants us to list each zero and its multiplicity, then determine whether it crosses or touches the x-axis at each zero. So every factor that has an x in it, we need to see where that is equal to 0. So my first factor with an x in it is x plus 2. Okay, x plus 2. So what's going to make that equal to 0? Well, so I'm going to go ahead and put my zeros here, make a little chart. My first 0 is going to be negative 2. My second 0 is going to come from this factor, x minus 3. What makes that equal to 0? Well, 3. So my two zeros are negative 2 and positive 3. Then it wants to know the multiplicity. So again, I'm just going to continue my chart here. The multiplicity of negative 2, again, it's the power associated with that 0. So the power associated with that is a 2. It's squared. And the power associated with x minus 3 is 1. Now I have to decide if it's going to cross or touch. Remember, we're looking at the multiplicity to determine that. If the multiplicity is even, so in this first one, the 0, negative 2, has a multiplicity of 2. Since it's even, it's going to simply touch the x-axis. And my other 0, 3, since it has an odd multiplicity, it's going to cross the x-axis. Now, the next thing they want us to do for part B is to find the maximum number of turning points. Remember, the maximum number of turning points is the degree minus 1. Now, in factored form, the degree equals the sum of the multiplicities. So that comes back from our definitions at the beginning of the section, okay? So we have our multiplicities listed here in part A. So my multiplicities are 2 and 1. That means my degree is 3. So the maximum number of turning points is 3 minus 1, which is 2. So this graph can have a maximum of 2 turns. All right? Part C wants us to describe the end behavior, so we have to do the leading term test. Now, when it's in factored form, it's actually pretty easy to come up with the leading term. You know that the degree is 3, so we know we're going to have an x cubed. That's going to be the highest power term if I were to go ahead and distribute this all out. Then you look here at the coefficient out in front. The coefficient is a 5. So if I were to distribute that all out, okay, FOIL everything and get it into standard form, my highest power term would be an x cubed, and that leading term would actually be 5x to the 3rd. Now, I see here that I have a positive leading coefficient and I have an odd, let's see if that'll work, and I have an odd power, all right? An odd power with a leading term that is positive, again, go back and look at your leading term test, odd with a positive leading coefficient is going to go down on the left and up on the right. Down on the left, up on the right. Now we're going to go ahead and we're going to piece this all together, okay, and do a little sketch of the polynomial. Now, I know, so I'm going to kind of do it over here. It's not going to be perfect, but I have to piece together what I know. I know that the zeros, or the x-intercepts, are -2 and 3. So let's go to -2 and put a point, and +3. Okay, so I know that those are the x-intercepts. I also know that the end behavior is going down on the left and up on the right. Okay, down on the left, up on the right. And then the last piece of information that I need to look at is whether it crosses or touches at each root. Okay, so at -2, at the 0 of -2, it says that it's just going to touch the x-axis. So I know I can go ahead and extend this arrow that's going down up to the root of -2, but it's not going to cross. It's just going to touch and it's going to bounce back. Okay, so I'm going to stop there for a minute. Now let's look at what happens at the next x-intercept, at 3. It's going to cross. So at some point, this has to turn back around. I don't know where, but it has to cross this x-intercept of 3, and I know that the graph has to end going up. So that's an idea of what the graph could look like. Again, I don't know exactly how far it goes down, down here in the at this turn, but I know that it has to cross the x-axis at 3, touch at -2, and be going down on the left-hand side and up on the right-hand side. So that gives you an idea of the what the polynomial would look like. Now that sketch is going to help us answer part E. Part E says, find the intervals over which the graph of f is above and or below the x-axis. So we need to look at when it is above the x-axis and when it is below the x-axis. Okay, so we have two scenarios. So I like to just start on the left-hand side, all right? So I'm going to try to highlight it for you, all right? This part of the graph right here, do you agree, hopefully, that it is below the x-axis? Well, it is, and then it hits the x-axis at that 0. So we need to write that section out in interval notation, okay? This section of the graph is below the x-axis, and I'm going to write that out as from -infinity up until this 0, so up until -2. And we're not going to include -2 because we're just talking about below the x-axis. Now my next piece, okay, is from -2, I'm going to trace the graph, everything from -2 until I get to 3. I'm still below the x-axis. So I'm going to do union. I'm going to pick back up where I left off, -2, all the way to 3. It's still below the x-axis. Now my last piece, I can see that it is above the x-axis, okay? This piece is above the x-axis. So I'm going to go ahead and write that out. That starts at 3 and is above the x-axis through infinity. All right, so we have one piece that's above the x-axis and two pieces that are below the x-axis. For example 6, we have a new function, and we're going to do exactly what we did for the last one. So we have several parts. This time, my function is f of x equals x minus 1 squared times x plus 3 times x minus 4. Now, we're going to use this function. First thing we're going to do is list the zeros and the multiplicities and determine whether it crosses or touches the x-axis at each 0. So when I look at my function, I see that I have one 0 here, another 0 here, and a third 0. Okay? So my zeros are, what makes this first piece equal to 0? -1. So my zeros are -1, -3, and +4. Then I need to list the multiplicity that's associated with each one. And then I have to determine if it's going to cross or touch the x-axis at each of those points. Multiplicities. The multiplicity that's associated with this x minus 1, we'll notice it's squared, so the multiplicity is 2. This -3 has a multiplicity of 1, and the 4 has a multiplicity of 1. All right. Whether it crosses or touches, we have to look at the multiplicity. Even multiplicities are going to just simply touch. Odd multiplicities are going to cross. Okay? Part B wants us to find the maximum number of turning points. Remember, the maximum number of turning points is the degree minus 1. When it's in factored form, remember the degree is the sum of the multiplicities. So in this case, we have the multiplicities are 2, 1, and 1. So we have a degree of 4. So 4 minus 1 is equal to 3. So the maximum number of turns we can have is 3. Now, when describing the end behavior, remember, once I figure out what the degree is, which is 4, I know that my highest powered term is going to be an x to the 4th. And I look at the leading coefficient, okay, I look at the coefficient out in front of my factored polynomial, and I see that it's just a 1. So I have an even degree, and I have a positive leading coefficient, which tells me that my function, or my polynomial function, is going to be going up on the left-hand side, up on the right-hand side. Okay, up on the left-hand side, up on the right-hand side. So now what I need to do is go ahead and do a little sketch. Let's piece it all together, all right? So I know that my graph is going to cross the x-axis or touch the x-axis at these zeros. So at -1, at -3, 1, 2, 3, and at 4. Okay, so those are my zeros. I also know that the graph is going to end going up on the left-hand side, whoop, and up on the right-hand side. Now I need to figure out what's going on at each of these zeros. So at -3, I know it's going to cross. So I know when I come down here, if I extend this arrow that's going up, if I extend it down, I know I have to cross at -3. Eventually, I have to come back up to -1, okay? At -1, it says it just touches it, so we're going to touch, and it means I'm going to bounce back down, and then I know again I'm going to have to come back up to my next root, which is a 4, and I know it crosses at 4, and then I continue my graph, okay? Again, I don't know exactly what it looks like, but that's the general sketch of what this function could look like. So that's part D. Part E. Find the intervals over which the graph is above or below the x-axis. So we need to see where is it above and where is it below. All right, so again, I like to just start from left to right. So right now, from left to right, it is above the x-axis from -infinity all the way until we get to -3. So it's above the x-axis from -infinity until we get to -3. And remember, we're not going to include that value. Then we see that the graph is below the x-axis between the next two zeros. So between -3 and -1, it's below the x-axis. All right, picking back up. From -1 until we get to 4, it's also below the x-axis. So union -1 to 4, also below the x-axis. And then my last piece, from 4 to infinity, is above the x-axis. So union 4 to infinity, that's also above the x-axis. Example 7, sketch the polynomial function using the zeros, multiplicity, end behavior, and the y-intercept. So we're combining it all. We don't have to do it part by part, but we're going to use all of those pieces we've been working on to sketch the graph of this polynomial function. So it says using zeros. So let's go ahead and find our zeros first. So we have zeros, and then we have the multiplicity, and then whether it's going to touch or cross. Okay, so we have three factors to deal with. We have this -2x cubed, we have x plus 1, and we have x minus 3. -2x cubed, when x is 0, that's going to make that term 0. So my first 0 is 0. The multiplicity associated with that is a cube, so multiplicity is 3. That is odd, so it's going to cross the x-axis at 0. My next 0 deals with this factor x plus 1. When I set that equal to 0, that's going to give me negative 1. The power associated with that is 1, so the multiplicity is 1. And again, since it's odd, it's going to cross the x-axis. And the very last one, x minus 3, that gives me a 0 of 3. Again, the multiplicity is 1. It's odd, so it's again going to cross the x-axis at that value. Okay, so we've taken care of zeros and multiplicity. Now let's talk about end behavior. For end behavior, we have to look at, get my pen to work. In order to figure out what's going on with the end behavior, we need to think about what the leading term would be. Okay, so I know that I add up my multiplicities and I will get to the degree. So this is going to be a function that has an x to the 5th term, 3 plus 1 plus 1. Then again, I look out here, I look in front, I see what is this coefficient out in front. It's a negative 2. So I know that if I were to take this function and distribute it and multiply it out to get it back into standard form, that my leading term would be negative 2x to the 5th. So I have a negative leading coefficient and have an odd degree. So negative leading coefficient, odd degree. So I got to think about what that's doing. That's telling me that the graph is going to go up on the left, down on the right. Up on the left, down on the right. All right, so that takes care of end behavior. And the last piece of information they tell us to find is the y-intercept. Remember, the y-intercept is when you plug 0 in for x. So we're going to do f of 0. That's going to give me negative 2 times 0 cubed times 0 plus 1 times 0 minus 3. Now this one comes out nice for us. Negative 2 times 0 cubed is 0. And 0 times anything is 0. So my y-intercept is 0. So I know that I'm crossing the graph at 0, 0. So let's piece this all together to see what this graph of this polynomial is really going to look like. All right, so we have 3 x-intercepts. We have the x-intercept at 0, at negative 1, and at 3. I know it's going to cross at all of those. I know it's going to end going up on the left-hand side and down on the right-hand side. All right, and now I piece it together. I know it's crossing each of those. So it's going to cross this first 0. It's got to turn back around so it can cross at the next 0. And eventually it's got to turn back around so it can cross the last 0. So that's an idea of what this graph could look like.